Pointer, good. And is this already on? Good. Is this okay?
Hey, we are starting.
Excellent.
Well, let's start. Good morning, everybody. Welcome to this morning session. And our first speaker is Mark Ediger. Please, Mark, who will tell us about something glassy, I suppose, but I have no idea what the title is. So I'll let you announce your title. Please, Mark.
All right. Can you hear me okay in the back? No. We don't think the mic's on.
Can you turn it off? Yeah. No, I think one has to do something here and turn on the volume. Is it that new?
I'm sure you haven't started the time yet.
Absolutely no.
Hello? Hello? Is it
Yes.
working now? Excellent. Great. Thank you. That's very helpful. Well, I want to begin by thanking the organizers for putting together such an interesting meeting. It's my first time in India, and I've really enjoyed it. The campus here is just a tremendous environment, and the meeting's very stimulating also. So I want to talk about glass. Actually, it's interesting, glass is in the title of the symposium. A lot of talks have not been about glass. Okay, so I want to talk about anisotropic glasses, and I'll explain what I mean by that. In particular, those prepared by vapor deposition. I have a faculty colleague, Lian Yu, who's been a partner in much of this work, and two of my former students, Kushal and Camille, have played a huge role in this. Kushal, by the way, grew up in Bangalore. Okay, we've seen this slide several times. Indicates that glasses are often made by cooling liquids. At some point, the liquid falls out of equilibrium, and we can get a variety of glasses here. That indicates glasses are non-equilibrium. That's really important for my talk. Another part of glasses is they lack long-range order, and I'm going to illustrate that with this X-ray scattering pattern here. And I want to explain what experiment collected this, because I'm going to show a lot of patterns that look like this. So this is a grazing incidence wide-angle X-ray scattering experiment. So we have a thin film, say on a silicon wafer. We bring the X-ray in almost from the side, and somewhere over there, there's a 2D detector. And you do a little correction to what the detector sees, and this is the scattering pattern that you get. You'll notice for this liquid-cooled glass, there are no sharp lines. So we lack long-range order. Okay, I've often made this point that even for a single component system, there are a lot of glasses. Okay, we can cool at different rates to get different glasses. We can cool and then age for different periods of time. We can cool, age, heat, cool some more. There's many complicated routes. In principle, all of those are giving us different glassy, non-equilibrium materials. So now this is going to really test my PowerPoint skills here, so hang with me. Imagine this plot, which is a plot of, say, enthalpy versus temperature, okay, which is like this. And now I want you to turn it sideways, because that's what I'm going to show you on the next slide. Okay, so there you have it. That's the plot we were looking at. And what I'm pointing out here is that there is another axis to think about when we think about glasses. There's an anisotropy axis, and all those interesting glasses that we were talking about on this slide are in a very boring little slice on this slide, okay? And so here is a scattering pattern from an anisotropic glass, and you can see what makes it anisotropic. Well, if I look along this direction, which is out of plane, I have a different structure than if I look along this direction, which is in plane, okay? So that's what we're going to talk about is anisotropic glasses. And what's out here, where these question marks are? So somebody is certainly thinking this. Wait a minute, aren't glasses isotropic by definition? So I want to just remind you that you all already know about some anisotropic glasses. For example, we've talked about strain-induced anisotropy already at this meeting. This is for a polymer glass. There's a stress applied. We get these colorful patterns when we look at it with white light between crossed polarizers, indicating that this material is birefringent, which means it's anisotropic. So this is an example of anisotropy which is induced after the formation of a glass. We can also have anisotropy which is induced as the glass forms, okay? And that's the case for these polystyrene glasses here. The polymer chains are oriented during injection molding, and then they're quickly cooled. That orientation is maintained, and that's the source of the anisotropy here. So in my mind, these are interesting examples that sort of prove the point that glasses we know about can be anisotropic, but these are very mildly anisotropic materials. And I'm going to be talking about materials which by some metrics are 100 times more anisotropic than these. Okay, so here is what I would like to do today. This is sort of going to be like zoology. I'm going to tell you about lots of different kinds of anisotropic glasses. There can be orientational order, there can be polar order, there can be sort of positional or translational order. A lot of these glasses are going to be made of organic semiconductors, and it turns out that the anisotropy is useful in the context of organic electronics, and I will explain that. And then I want to end with some, what I think are some interesting fundamental questions about anisotropic glasses. Okay, so I'm going to talk about materials made by physical vapor deposition, so I should explain what that is. You have a vacuum chamber, you have a substrate, the temperature of the substrate is controlled. The substrate is cold enough that when molecules from the vacuum, from the vapor in the vacuum, hit the surface, they condense. They stick with a 100% probability. So the substrate temperature is a key parameter that we'll talk about that controls what kind of amorphous material we make here. I mean, you could make a crystalline material, but we're working with good glass formers, so we make amorphous materials. The deposition rate is the other key control parameter, which I'm not going to talk about very much. And this is what the vapor deposition chamber in my lab looked like. Okay, so let me just start out with an overview of the kinds of anisotropic glasses that can occur. So this is sort of a picture gallery, and this is from the work of Kushal and Camille. So let's start with this molecule here, which is ALQ3, which is an organic semiconductor. Actually, in 3 dimensions, it looks pretty close to a sphere, so we're going to think about it like a sphere. If you spin coat that from a solvent, you get an isotropic material. You can see that here, a lot like a liquid-cooled glass. On the other hand, when you vapor deposit the same molecule, you get this scattering pattern. And the fact that there's some extra intensity here in the out-of-plane direction, whoops. Whoa. Yeah, I didn't realize this was going to advance the slides, but it is. Okay, cool. There's extra scattering here, and the Q value of this scattering tells us that there's some sort of layering of these spheres in this deposition. So qualitatively, it looks something like this. If we deposit rods, they might decide to lie down, in which case the scattering looks like this. You can think about this is basically the nearest neighbor distance here. In this direction, there's a lot more nearest neighbors at that distance than in this direction. That's why there's a lot more scattering here than here. And then, so this is orientational order. This is some sort of translational order. This has both. So now we have rods that are standing up. So this scattering gets pushed down to here. And then we have sort of these diffraction lines consistent with a sort of layered structure. Okay, so this is just to sort of get you warmed up about what can happen when you vapor deposit organic molecules. All right, so now let's start talking about molecular orientation, which was the first kind of anisotropy I want to discuss. This molecule here is an emitter used in OLEDs. I'll talk about that a bit more in a minute. And all I want to illustrate here is that substrate temperature is a really key variable. Okay, so these are two identical depositions. The only difference is the temperature of the substrate during the deposition. And you can see from the little cartoons here qualitatively what's going on with the molecules. Turns out this is a great orientation to make OLEDs work better, and there's a community of people who are working on that problem. Let me just explain why that's the case. So my cell phone, and probably every cell phone in this room, has an OLED display. It's an organic light-emitting diode display. And this is sort of a simple view of what one pixel looks like from the side in an OLED display. And for our purposes, this is the important stuff. These are the active layers that make the light come out of the OLED, and they are vapor-deposited glasses of organic semiconductors. And this is about 20 nanometers. Each of these layers is about 20 nanometers thick. There's an electron transport layer, a hole transport layer, and these combine in the emitter layer and produce emission from a molecule that might look like that, for example. Okay, so let's think about the difference between having these rod-like molecules in this arrangement or in a random arrangement. Just empirically, it turns out you get much higher charge mobility in this arrangement by more than an order of magnitude. But the more important factor for OLEDs is just a sort of a trivial geometric thing.
I'm sorry, what are the layers between the anode and the cathode? I think I understood.
This is an electron transport layer, an emission layer, and a hole transport layer. Okay, but for the purposes of this talk, they're all just layers of different vapor-deposited glasses. Okay? Okay, so this molecule has a transition dipole for emission along this long axis. So if you have a random arrangement, some of the molecules have their transition dipoles in this direction. And when they emit light, it goes completely sideways into the film and doesn't go out, which is useless for an OLED. So you don't want any of those molecules with that orientation. You want them all lying down. And if you can do that, you get 50% more light out of your OLED for exactly the same electrical input. And so there's been a lot of engineering in order to figure out how to make this kind of anisotropy in vapor-deposited glasses. And I just want to mention Daisuke Yokoyama, who really was the first person to start to investigate this kind of anisotropy.
So Mark, this has pneumatic order.
You can call it pneumatic order, sure. Yeah, fine. Okay, I know physicists love to estimate orders of magnitude. Okay, so I'm going to give you maybe 10 seconds to think about this.
10 to the power 10.
10 to the 14? How many OLED displays are made each year by physical vapor deposition? So just to be clear, my phone counts as one. This is one OLED display, okay? All right. 10 to the 9, okay? It's a global market of $50 billion, and it's all based on anisotropic vapor-deposited organic glasses. Okay, so, oops. Why not crystals? Partly because they have rough surfaces, which is bad. You get pinholes, and then the charges find a way of recombining without light coming out. Partly because they're polycrystalline, and that makes one pixel different from another. And so those are probably the main factors. Yes, the deposition rate is important. Well, they're not crystals, and so the layer by layer growth isn't quite the way you would think about it. Okay, I wasn't going to go into this, but to a first approximation, substrate temperature and deposition rate are coupled variables. And let's just leave it at that. Okay, you're seeing all the important trends just by looking at the substrate temperature. Okay. All right. So back to molecular orientation. So we're going to switch experimental techniques here, and I'm going to be using spectroscopic ellipsometry to learn about molecular orientation, which is just an ellipsometer that uses many, many wavelengths. From that, I get both the real and the imaginary parts of the index of refraction as a function of wavelength. And from that, I can evaluate the dichroism, which directly tells me about the orientation of the transition dipoles. And that's what's shown here. It's given in terms of an order parameter S, which is just the average value of the second Legendre polynomial. So S is bounded by 1 above. That means everything's pointing straight up. And it's bounded by minus 0.5 below. That means everything's lying in the plane, okay? So this is a measure of transition dipole orientation. This is the birefringence of the films, which is the difference of the index of refraction out of the plane of the film and in the plane of the film. Yes?
So when you squeeze on these OLED displays, you see like the pixels getting blurry, and then they immediately do echoes. And if it's glassy, how does it come back to the exact echo?
Actually, I don't know what happens when you squeeze, but I don't think you're deforming these glassy layers. So these are high modulus layers, more than a gigapascal. So you're probably deforming something else in the circuit, which is causing that problem. Yeah. Okay, so back to molecular orientation. These are two different measures of anisotropy of slightly different things, but clearly closely related. So 3 molecules, data for 3 molecules is shown. The details aren't so important. Think about this as a short, medium, and long rod, okay? So one important point is that at low temperatures here, we can achieve order parameters like minus 0.4. So minus 0.5 would be perfect for OLEDs. And so this graph basically gave a recipe for people who are trying to design better OLEDs, and they've been making use of this in order to achieve the orientation that's most favorable. Another thing to notice is that these 3 rod-shaped molecules sort of show a generic pattern in terms of their anisotropy. We actually understand where that comes from. It can be reproduced in coarse-grained computer simulations, and my collaborator, Juan de Pablo, did those simulations, and we wrote a paper together about that. The third point I want to make is that the birefringence here is really substantial. It's 0.2 in index of refraction units. So those earlier examples that I showed you about like stressing that disk, the birefringence was probably 10 to the minus 3. So this is like 100 times bigger than that birefringence. And if you want to know what this point here looks like, 0.2, that is this much vertical orientation. And if you want to know what minus 0.4 looks like, that is this much horizontal orientation. Okay, so I think this is a fun experimental detail. You notice there are many, many points there. I didn't actually say this. This is the substrate temperature. This is really important. We're controlling all this with the substrate temperature. When you deposit above TG, you get isotropic materials. Just below TG, molecules stand up. Further below, molecules lie down. You'll see many, many substrate temperatures here. We can do experiments 1 substrate temperature at a time, and we do. But it's more fun to take your substrate and clamp the 2 ends at 2 different temperatures, okay? And then you make a gradient in temperature that you can calculate. In this case, it's about 100 Kelvin gradient, and you hold that gradient constant during deposition. And so you make, in one deposition, a whole library of glasses, actually, that covers most of the data that I showed you in that last plot. Okay, so this is just a photograph with a phone and white light from the lab lights. The fact that the color is different over here than here, this is almost completely due to the birefringence of the samples. So with your own eye, you can see huge changes in the optical properties as a function of the substrate temperature. What? That is an American dime, which is about this big. So this distance here, as I recall, is something like 5 centimeters.
Did you analyze the surface roughness while depositing?
We analyze the surface roughness after deposition, and these films,
Or while growing?
we don't do it during deposition. I'll tell you, if you stop at various points, what you find is if you deposit just a little bit, it's super rough because it hasn't yet formed a continuous layer. By the time you're at 100 nanometers, most of these films are 100 to 500 nanometers. They're incredibly smooth, less than a molecular thickness in terms of smoothness, which is, again, part of why they're good for OLEDs. Yeah. Okay, so that was orientational order. Okay, so now I want you to imagine that I have molecules that have dipole moments, and many organic semiconductors do. And now I want to talk about the orientation of the dipole moments in the vapor deposited film. Now, if I had a liquid-cooled glass with molecules with big dipoles, they would all cancel out, or almost completely cancel out. The macroscopic dipole would be essentially zero because they would point in all directions. You might think that would happen during vapor deposition, but it doesn't, okay? So you can make materials in which there's a macroscopic dipole as a result of the deposition process. And so I've indicated that schematically here. What's shown here are 7 different molecules. As a function of thickness, this is the surface potential. So the surface potential is a direct measure of how much dipole orientation there is in the film. So people that do, surface physics, they report surface potentials of a few millivolts and are analyzing that. These surface potentials are like 15 volts, okay, for a 200 nanometer film, because it's not just the surface that has these dipoles aligned, it's the entire film that has these dipoles aligned. And since this plot was made, people have refined this. And so in a 200 nanometer film, you can now hit 60 volts, okay? So it's a big effect. There's a community of people in organic electronics that study this. This effect is called giant surface potential or spontaneous orientation polarization. And in terms of a metric, the average of cosine theta for the dipole moment can be as large as 0.4. So 1 would be everything perfectly pointing. We can hit almost half that by the deposition process. And this has an impact on the operation of OLEDs, and so that's one of the reasons people are interested in it. People also have some ideas for other organic electronic devices that would be based on this effect. So this is another different kind of anisotropy. It is continuously tunable with substrate temperature. So on this slide, I'll illustrate first that. This is a plot of surface potential versus thickness now for just one molecule at 4 different temperatures, and you see 4 different slopes. Okay, so this is essentially analogous to what I showed you earlier for the molecular orientation. There's some very clever people working in this field, and there's one guy, Masaki Tanaka, in Japan, and he read one of our papers, which said that everything, all the order is controlled by what happens right at the surface during deposition, because we have a highly mobile surface, and the molecules are trying to equilibrate in a highly anisotropic environment, and then they get trapped. And so he reasoned that if he could take molecules that had fluorine groups on them, that he could control the orientation of the dipoles in the films, because fluorine in any molecule wants to point out into the vacuum. So I'm sparing you the chemical details here. This is a physicist's molecule. It has a dipole moment and a CF3 group. Or the CF3 group's on the opposite end, okay? And when he makes molecules that look like this, he gets a positive surface potential. When he makes molecules that looks like this, he gets a negative surface potential. So everything in this process is being controlled by what the molecules are trying to do right at the free surface during the deposition process. And then as soon as they're 1 or 2 layers below that, they are stuck because they've lost their mobility. And that's why we can continue to add layer upon layer of these dipoles and get this huge macroscopic dipole.
So it forms a template from which then the rest is kind of growing in a way in terms of the dipole alignment.
No, it's not a template. I mean, well, you can say the interface is a template.
Yeah.
Yes.
Yeah.
But the material below is not a template. So if you change the temperature in the middle of the deposition, you change to a different degree of alignment, because it's controlled by the free surface at that new temperature. Okay? All right. So the last kind of order I wanted to talk about was translational order. I'm going to have to speed up a little bit, I think. And so I want to compare two molecules that we think of as siblings because they're very similar in terms of their shape and chemical functionality. The differences are circled in red, if you care. The important point is that this molecule is a mesogen. It has equilibrium liquid crystal phases. This one does not. And you can see that here in the DSC traces. As you cool this molecule, you go from isotropic to pneumatic to smectic to a smectic glass. This molecule is just an ordinary glass former. So we're going to vapor deposit each of these molecules. Let's start here. This is the mesogen. This is itraconazole. So this is the scattering of a smectic liquid crystal of an aligned smectic liquid crystal because the orientation has to be the same everywhere in the film. And I think this is already pretty amazing that you do nothing more than throw molecules down on a surface in a vacuum, and they achieve this beautiful packing, which is indicated. These diffraction lines here tell you about this spacing, and as I mentioned, this is telling you about the vertical orientation. So that's cool. I mean, and you can do this on a wafer as big as you like. So everywhere on the sample, you're getting this orientation. The more amazing thing, though, is that you can do this for a molecule that doesn't have any equilibrium liquid crystal phases. And it still gives you something that looks like an aligned smectic domain. And so I think it's useful to understand how this happens because it'll give you more insight into the deposition process. For the mesogen, itraconazole, this is what the equilibrium looks like at the free surface. Okay, we know that it anchors like this. This is the free surface. So during deposition, you know, a layer goes down. It's perfectly happy to be anchored like this at the free surface. The next one is also happy, and you build up this layering. So that's cool. Posaconazole. We know the equilibrium liquid is isotropic, so I draw this here. But in order to explain the results, I have to hypothesize that the top layer still looks like this. Okay? And then if that were true during deposition, I would always get an aligned top layer. I'd get layers below, which in some sense are unhappy. They would like to become isotropic, but by the time they realize that, they've run out of mobility and they're stuck. And so that's how we get a smectic arrangement here. And after the fact, we did Nexaf's experiments that verify this orientation at the free surface, so we know this is the correct story for how this works. And this. So this is inferred from the fact that it has no liquid crystal phases, and it's an isotropic liquid. Okay, so we did not, I mean, I guess we maybe didn't verify that so directly experimentally. This is the part that we verified experimentally. Yeah. Okay, so these things have interesting anisotropic mechanical properties. And I'll just show you one study that we did. This is itraconazole, the one that makes liquid crystals. 3 different deposition temperatures, which are clearly giving me 3 different structures. Here we have basically the perfect smectic monodomain. Here we have the molecules lying down. And then with my friend George Fetus, we used Brillion light scattering to completely determine all the elements of the elastic stiffness temperature in these anisotropic materials. And I'll just show you the Young's modulus. We know all the moduli. This is the out-of-plane Young's modulus. This is the in-plane Young's modulus. I'll just focus on the smectic, the thing that looks like a smectic. This is roughly a factor of 2 difference in the moduli, which it turns out to be a really big number. It's similar to the difference in the parallel and perpendicular moduli for highly oriented and partially crystalline spider silk. So these things have quite anisotropic mechanical properties. Okay, so I just wanted to summarize before I get to the questions. I've given you examples of 3 different kinds of anisotropy that can happen in vapor deposited glasses. In each case, I've gone to some effort to try to convince you that the anisotropy is substantial. We have this P2 order parameter. We can get pretty much completely maxed out in terms of the molecules lying down. We can get sort of half of the total possible alignment for dipoles. We have substantial smectic order, and we have a big anisotropy in the moduli. In every case, we can tune the anisotropy by substrate temperature or deposition rate. For some of these cases, these are critical variables for OLED performance. We have this mechanism about equilibration happening right at the free surface, and that at least qualitatively explains what I've shown you today, in some cases semi-quantitatively. We know enough about the process that we can design molecules to optimize the anisotropy. And just to come back to this point, the mechanism we're talking about here is really not substrate epitaxy. It's really about what's happening at the free surface, not what's happening with whatever you started with. Okay, so I just wanted to spend the last couple minutes. I think there's some interesting questions in this vast array of glasses which are fairly unexplored. And so one is, what's the interaction between glass stability and anisotropy? So I should tell you that PVD glasses can be the most stable glasses prepared by any means. I didn't really talk about that today, but that's another part of the story. And they can simultaneously be the most anisotropic, I think. And so one view in the literature is that one causes the other. The anisotropy causes stability. I don't think this is right, but it's an interesting idea. It seems odd because thermodynamically it must work the other way. You must have to pay a free energy cost in order to produce this substantial anisotropy, but we really don't know how big it is. So I think that's an interesting point. And then there's the kinetic stability, which does not have to follow the same rule, and we don't know about that. My hypothesis is that even substantial anisotropy doesn't have much impact on stability. And that would be sort of cool from an engineering perspective, because it means it'll be easier to produce. Maybe you don't want to do vapor deposition, but if you have some other means, you don't have to bias the system very much in order to come up with a substantially anisotropic material. Okay, so I think that's an interesting question. And then another one that I've thought about is, okay, I should just take a step back. Part of what I like about these anisotropic glasses is they sort of blur the distinction between a traditional glass and, how long have you been doing that? They blur the distinction between a traditional glass and a crystal. And they're sort of hybrid materials, and I'm really happy that there's some ambiguity and some blurring in there. But one of the key reasons glasses are used in applications is because they're macroscopically homogeneous. And I just have a feeling that if you make a sufficiently anisotropic glass, it's going to start breaking up into domains, and you're going to lose that. But I don't know when it happens, and I just use this as this is actually a 2D simulation that sort of illustrates the beginning of domains. And I imagine this is what happens when we vapor deposit rod-shaped molecules and we make them lie down in the plane, that they have to take up arrangements that look sort of like this. And then there's now a characteristic length scale, and I don't know about the energy of grain boundaries, but that will control whether these things are homogeneous or not. So I will now stop, because Luca's exercised over there. You've already seen all this. I'll just leave this up as a summary. Thank you.
Thanks a lot, Mark, for this really great talk. Questions?
So recently we looked at, from simulation perspective, so a model glass former with spheres, that's a Cobb-Anderson-like thing, and then you add, dope it with rod-like objects or particles, then you see that it actually enhances the stability, and if you make the rod size bigger and bigger, then it can actually take you to nearly ultra-stable-like situations, which are in terms of, let's say, breaking. If you shear it, it will have a very clear shear band, and by analyzing various quantities, we came to the conclusion that this comes from the loss of rotational degrees of freedom of the rod.
Okay.
And is this something that
Well, I would say, I mean, I think it's very interesting to try and make ultra-stable materials by different procedures. And so I'd say, you know, you're making a relatively boring glass to start with, and then you're sort of doing something artificial to turn it into a special glass.
No, you just, like, so while processing it, you can actually add few
Yeah,
molecules.
and I'm just saying, what we're doing is slightly different because we're not changing the molecules, and we're doing you know, we create the stability as a result of the process of making the glass.
But if you deposit two types, one is a sphere and another rod-like, and deposit together.
I see. Okay. All right. I didn't understand that. Well, that's interesting. Yeah. I mean, we've done mixtures. We have 10 papers about all this with mixtures, but I thought I would keep it simple and just tell you about the single component systems.
Okay.
Yeah, very interesting. I was especially intrigued by your last slide. So the half crystal, half glass. And I do have spy topological defects in this thing. And sort of, how would you define the border?
Let's see. Where am I going the wrong direction here? There we go. I don't know. I mean,
Yeah.
this is just really artistic inspiration. I just wanted to have an image to give an idea of what I was thinking about. I don't know how to define any of this. But it seems to me that something like this is probably happening and would be interesting to explore.
Yeah, there's a very lively discussion in the cells on surfaces community on more or less this topic.
So if what I don't understand is maybe the terminology of anisotropic glass versus liquid crystalline glass or something like that.
Yeah.
If you take a pneumatic, you know, which in equilibrium would be a liquid in for translational order, and you quench it,
Yeah.
don't you form the same type of glass?
So in fact, I showed you that. Sorry, you have to go through this. There we go. Yeah, so in this example here, you have an isotropic liquid which turns into pneumatic, which turns into a smectic, which turns into a smectic glass. This would be a smectic glass that has zillions of domains with many different orientations. It would not have one domain perfectly
Okay, so
oriented.
that's the one. Okay,
So that for the liquid crystal case, that's the distinction. But in the other case, we take a system that has no liquid crystal phases, and we produce all this smectic order.
but then could we think of the fact that the fact you have a unique domain is because you have an effective external field that forces all the domains to align?
Sure. I'm good with that.
And presumably because it doesn't form the smectic before, right? Yeah, no question.
So, Mark, this is a good slide for my question. So, you know, if you have a fluid state, I mean, a liquid state, you could induce anisotropy in various ways,
Yes.
and that's not necessarily so, you know, unusual.
Yep.
I guess the thing that is special in everything you're talking about is that anisotropy gets frozen in. And so one interesting question one could ask, especially in the context of a system like this, where possibly you go from the isotropic or the pneumatic phase and you jump a phase transition and get into a frozen state. What happens over time through aging in the system exploring sort of the lower temperature phases?
So let me try and translate your question into what I was thinking. So one of the possibilities we considered is that since the deposition process essentially equilibrates at a lower temperature, is that there is a true phase transition, in this case, to a liquid crystal state, and it's just out of reach, just below the ordinary glass transition temperature, and we accessed it. I think that's a plausible interpretation of the results. We took this ordinary glass at 5 degrees below TG and aged it for months and did not see the appearance of that, but that wouldn't, strictly speaking, rule it out. I don't think that's the answer. I mean, we don't need that to explain the results. That's too exotic, I think. And so, but it could play a part. I mean, I don't think I could rule it out.
Okay, I think that we should thank Mark again and move to the next speaker, Paddy. So the next speaker is Patrick Royall. And again, I don't know the title of his talk, so he will announce it.
There, you got that. All right, good.
Okay, so good morning, everyone. It's a real pleasure to be here. I'm very grateful to the organisers for inviting me, and yes, it's really great to be back in Bangalore and with such a esteemed audience to talk to. I've been really blown away by the talks, by the quality of the talks at the meeting so far. So I'm going to talk about structure, and what I'm going to try to do is to talk to two audiences, because some of you are, well, some of you have seen me before and have some familiarity with the history of this, and some of you haven't. Okay, so I'm going to try to bridge the idea of giving something holistic, which will mean that I will need to say some stuff that I've already said previously, and also present some new material towards the end of the talk. So I hope that's okay. And so what I'd like to start with is by acknowledging those who've done the work. A lot of this was work of PhD students, Alex Malins, Livka Ortlieb, more recently Dan Chilang was a master's student with me in Paris, and James Hallett and Francesca Tucci were postdocs. I should particularly mention Trond Ingebrigtsen. I asked Trond for a photo. This is what he gave me. But anyway, there we go. Thomas Beck is a long-term collaborator in Stuttgart, and also Gilles is not named, but I will briefly mention some work that we did. Okay, so these are the bodies that paid for what I will talk to you about. And what is interesting about glass physics? So I'm going to try to outline why I love glass physics, and I'll just mention we have a review. So this is it was mentioned that 2022 was the year of glass. We almost made it in the review, but that's what we were aiming for. It was universality across molecules and colloids and grains. So we argue here that they all behave in the same way. So I hope that sort of falls into the unifying concepts. But for me, and not only for me, because other members of the audience have put this book up as well, so perhaps for the younger members of the audience, I would emphasize to read this book about scientific revolutions. So glass, for some time, has been a scientific revolution. Ludovic mentioned this article in the New York Times. I'm going to take some other quotes from it, such as one of my great heroes, Peter Harrowell, who said that the microscopic structure should determine the microscopic properties. And what we've seen, for example, in Patrick's picture of having exactly the same picture for the glass and the liquid, is that looking at the structure is not straightforward. And so there's this idea that the arrangement of atoms and molecules in the glass is indistinguishable from that of the liquid. And we've also understood that there's plenty of room for contentious disagreement in the field, and I'll try to give my own personal perspective on that on the next slide. And also David White, for anybody who doesn't know, is an experimentalist, but he argues that there are a lot of different theories for the glass transition. And so why is this? This is because there are theories which are based on incompatible assumptions which nevertheless give identically good descriptions of the available data, which is not really a great situation. So what can we do? we either have better data or better theories. And I will look at the top. So I started getting involved in glass sometime around here. Now, does anybody know who said this? He said this at least twice. Julio does. Great. Okay, it was Wilson Poon. So this was in connection with the reentrant glass transition in sticky spheres that the Edinburgh group had found around that time. We then have geometric frustration, and if I may, the godfather of geometric frustration is in the room, and I'll talk a little more about that in a moment. And then we move on to the period that I have heard mentioned. I didn't come up with this, I don't know who came up with this, but the glass wars. And there are individuals in the room who know much more about this than I do, but I won't say very much. But I will say, I presume others have seen this. This was pinned up in the chemistry department in Berkeley, where David Chandler, who's pictured here, had his lab, and it's still there, okay? It's at least, it was still there. I took this photo a year ago. So this is Juanpe Garajan, a rather younger Juanpe Garajan, and he's saying we've made some progress. Does anybody know how David Chandler replied? Exactly, Mark. Yes. Yes, so this is the situation as far as the Berkeley group are concerned in the noughties, that, you know, we're all good, much as Peter Wolliners was 20 years earlier. Okay, so that was the period of the glass wars. We then had the Simons period, so clearly there are people in the room that were actually involved in that. So a lot of things happened, and now I would say that we've been hearing quite a lot about dynamic facilitation, which was what the theory that the Berkeley group around David Chandler developed somewhat earlier. So I'm going to talk to you, though, about structure. I think the purpose of this was to give some context that there's a lot of different ideas around, and these are just a few of them. So for me, structure goes back to Charles Frank, and Frank argued that there are 3 ways of organizing 13 Leonard-Jones particles. There's the face-centered cubic, the hexagonal close-packed, and there's another body which has 5-fold axes, which are abhorrent to crystal symmetry, and that's the icosahedron, which is pictured here. So this is a little bit like a 3-dimensional pentagon, and for me, it's the origin of structure in glass. Frank argues it's 8.4% better in binding energy if I have 13 particles. So this is the minimum energy structure for 13 Leonard-Jones atoms. Now, it actually turns out it's not that popular in the Leonard-Jones liquid, but never mind. It looks like this, and what we did then was to extend Frank's ideas and start to look at different numbers of particles. So here's 5, 6, 7, and so on. But we could extend it further and take these particles here, and we would go and look for these clusters in sets of coordinate data, which might come from simulation or might come from colloid experiment. And so these are minimum energy clusters of the Leonard-Jones model. We can also look at minimum energy clusters of the Morse potential, which is a variable range, as indicated here. The numbers are the number of particles, and the letters refer to the range of the Morse potential in question. And so when we looked in certain fairly common glass formers like the Wangstrom model, the Cobb-Anderson model, hard spheres, they all turned out to have the particular so-called locally favored structure. And so we studied this, and I've talked about this sort of thing before, and one of the comments when I'd be questioned, which is very reasonable, said, yeah, that's nice, but if we're thinking of you know, we're looking for universality, and this is not universality, right? You've looked at 3 models that you've cherry-picked, and so that's a very fair criticism. So what we can do is these are the minimum energy clusters for a particular material. We actually looked at the binary Leonard-Jones glass formers as well. It turns out these are other clusters This is also a minimum energy cluster for the Cobb-Anderson model, for example, but these are other clusters of binary Lennard-Jones glass formers. We also looked at dipolar colloids, which are a naive colloid physicist step towards molecules, and we actually started looking at something towards real molecules as well. So my point is that the method can be applied to, in principle, whatever material you fancy. So how does it work? We take some coordinates.
Sorry, just to clarify. I mean, you said minimum energy clusters. So are you talking about isolated clusters or the clusters you find in the liquid? I imagine
Very good
the
question,
latter, right?
Sri, and I'm sorry I wasn't clear. So we are looking at, these are minimum potential energy clusters of this number of particles for whatever material it is. In the case of hard spheres, we look at groups of hard spheres, and we look at the minimum free energy clusters in a mean field surrounding. So we can interpret hard spheres as well with a similar methodology. But then we take some coordinates like these, and we look for structures that have the same bond topology. So the pink here is these octahedra, and the green are these defective icosahedra, and so on. Okay, and the red are these pentagonal bipyramids with another particle stuck on. So we can identify these different clusters in the coordinate data set that we would obtain by either experiment or simulation. Well, this also looks a bit of a mess. Okay, we could make it look less messy by saying if the cluster is five-fold symmetric, i.e. it has a five-membered ring, then we'll color it green. So now we see there's a lot of five-fold symmetry in this data set. Now, how do we know which of these many clusters is the locally favored cluster? That we measure the lifetime. Okay, so here they've measured the lifetime of, in this case, it's the icosahedron that Charles Frank talked about, which is the minimum energy, the locally favored structure for this particular glass former, the Vangstrom model. So that's all fine, and we can look at the fact that at high temperature, we see few of these icosahedra. We drop the temperature, we form a network of icosahedra. And we can see that this is the angel plot, and as it becomes super Arrhenius, then we start to see, below the onset temperature, is when we start to see these clusters forming. So that's all fine, but does that prove anything? I mean, it's just that, you see more of these clusters as you call the system. So if we want to look for some causality, then we could look at the theory of geometric frustration. So very briefly, the idea, as I understand it, is that imagine that there's a non-frustrated scenario. So I said that these icosahedra, they're like three-dimensional pentagons. They don't tile space. And so but imagine they did. Imagine there was a situation where that could happen, and you drop the temperature of the system, and it would crystallize into a set of icosahedra. And so it turns out this does happen in the case of 120 spheres on the surface of a 4D hypersphere. So that's what we'd expect in that particular case, and we could look at it, for example, with classical nucleation theory. We'd look at the size of some crystal, as it were, of icosahedra. But of course, in reality, in Euclidean space, then we have a frustration term which comes in like this. And so the picture is that we have, in the unfrustrated case, then there's the crystallization, so to speak, but in reality, we've got an avoided transition. But the question is, can it influence, nevertheless, what we see in the Euclidean space? Well, it works beautifully in tightly curved space. So I said there's 120 spheres on the surface of a 4D hypersphere. That's actually really tightly curved, okay? As we uncurve the space, it turns out that the picture breaks, and it's certainly not the full story. So, okay, that's one possibility. I've said that we've been hearing quite a bit about facilitation recently. Here are just a few papers that talk about it, the dynamic facilitation picture. And what we did some time ago was this is not us, this is the Berkeley Group's movie, But this is the picture of facilitation, that there are red particles that are moving and blue particles that don't, and somehow the red facilitate the movement of other red. But you can see that here there's a region that doesn't move, and here there's a region that does move. So this would be like a liquid, this is more like a solid. And so in the picture of facilitation theory, we can imagine many trajectories. These trajectories are quite small, and some of them will move, and some of them don't. And so if we could we could consider the case of here's a trajectory taken for a small system over a relatively short time, and this one's active. It's not active matter, it's just moving. This is inactive, more glassy. And so you might imagine that there'll be some that move and some that don't, and there's a distribution of them, which is illustrated here. What's interesting in the theory is that there is supposed to be, under a dynamical field, a phase separation to an inactive phase and an active phase. This was shown to be the case by the Berkeley group in this paper here, and what matters is the shoulder here. And when the field is applied, then you get an inactive phase and a normal liquid, and they are coexisting, and you can demonstrate that it's a dynamical phase transition. We did the same thing, but with the structure. So in other words, what we found was that without the field, or our related field, then there's a shoulder here in the blue data, and then when we apply the field, we get this phase coexistence between a phase that's rich in local structures and the normal liquid. So this actually demonstrated that there's some kind of clear coupling between the structure and the dynamical properties of the glass-forming system. So something worked. But, and I'm particularly pleased to be able to show this slide here, the elephant in the room, which is we'd heard in some of the previous talks, is that everything I've talked about so far was done some time ago when we were not able to supercool things much beyond the mode coupling transition. So everything I've talked about is, not very deeply supercooled. In fact, it's up to about here, okay? So what we'd like to do is to get more deeply supercooled, and so we did better by using the nanocolloids. What I mean by that is the colloids, the timescale goes with the cube of the particle diameter, and so if all we have to do is use smaller particles, and we drop the particle diameter by a factor of 10, which then gets us about 3 decades up this plot. So we get about 3 decades past the mode coupling transition with the nanocolloids. It's not easy, but you can read about it here. What did this tell us? Well, it told us there was more structure. That's around the onset temperature, that's around the mode coupling, the onset volume fraction with its colloids, with the control parameter is volume fraction. This is around mode coupling, and this is about 3 decades past mode coupling, so we see more structure. So that's fine. We also see a drop in configurational entropy here. But I wanted to talk to you actually about the simulation work, because that's a bit newer, and what we showed with the simulation work is a little bit the issue that I started the talk with. These are in principle mutually incompatible interpretations. This is dynamic facilitation, and it has this prediction for how the relaxation time increases. This is the Vogel-Fulcher-Tammen, which is loosely related to a thermodynamic picture, and they both give an equally good fit of the data. This does not matter, okay? But both of these interpretations are absolutely fine. But what I want to talk about more is this one, and what is the mechanism of relaxation in the dynamic facilitation picture. So the unit of relaxation in facilitation is an excitation. An excitation is a local single particle relaxation event. These occur on microscopic timescales, and we came up with a recipe to measure them in the glass forming liquid. The recipe is based on this paper. I will emphasize that it wasn't as easy as we thought to develop it. I said to the student that she'd have it done in an afternoon, and 6 months later, we were still going, so I was in trouble in that for that. But nevertheless, the timescale is relative. But nevertheless, we developed a way to identify these excitations. So I'm just going to show here. This is the trajectory of a particle. It jumps to another point and it stays there, and we can measure the timescale over which it does that. So this would be a bad excitation. It moves too slowly. This is a bad excitation, so not an excitation. This one's also bad. It doesn't commit to the new place. It moves and then goes back. But this one would be good. It jumps quickly and it stays put where it should be. How long have I got, Luca? 5 minutes. Okay. 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 Very good. All right. So what the excitations look like then. So this is a movie of one of the simulations, and we're about 2 decades past the mode coupling temperature, and the duration of this movie is about 1/10 of an alpha relaxation time. The pink particles are in excitations. Occasionally you see and I leave them pink if they've been in one. When they enter into an excitation, they are red. So I start the movie, there's a red particle that then becomes pink. And they're not distributed homogeneously through the system. So this is the emergence of some mechanism of relaxation in the material. Now, the second elephant in the room that I must tell you about is that these excitations, I've mentioned, they have a microscopic time scale and a microscopic length scale. And in the context of the glass transition, where time scales become huge, this has this is something I think deserves some attention. So what do I mean by a microscopic time scale? Here, I mentioned there's this thing, delta T. This is the time scale of the excitation. And at high temperature, there's a distribution. There's also a distribution at low temperature, but it seems that the long delta T tail is going away at low temperature. What I mean by this is that the excitations get become a little bit shorter at low temperature. So as we drop the temperature, there is a massive decoupling between the excitation timescale that's stuck here at about 10 Lennard-Jones time units and the timescale associated with dynamic heterogeneity, or indeed this so-called cooperatively rearranging region timescale. So by the time we are coming here, there are a vast number of excitations that we can have in between the relaxation of the whole system and the relaxation of an individual particle. So let's go back to this idea of the excitations and the structure. All right, so I said I was going to talk about structure. The excitations were built in the dynamic facilitation picture, which we have heard was based on ideal kinetically constrained models, which are ideal gases. So in principle, the excitations should have nothing to do with structure. Well, what can we see? So I've said that it's not a surprise that the population of local structures increases as I drop the temperature and I increase the relaxation time. So what we'd expect if the facilitation picture in its naive sense was correct is that there should be no correlation between these and the excitations, but there is. So the probability that if a particle is in one of these, that it's in an excitation, is if there was no correlation, this would be 1, it drops. Okay, so it's becoming less, as we supercool the system, it's becoming less and less likely that an excitation particle is in a local structure. So the semantic correlation, which is unexpected in a sense, but certainly these are definitely influencing where the particles are relaxing. And so if I'm now showing a series of stills, so this is the same movie that I just played to you, but I'm showing in blue here particles which are in a local structure, and the pink here are the emerging excitations. The white is when it's in both, all right? So occasionally a particle is in both a local structure and an excitation, but usually they are separate from each other. So somehow the excitations make perhaps something towards a network that finds its way around the regions that are in the local structures. So what we have is that if we could measure this a little more carefully, then the red particles here are excitations, and we're going to measure D, which is the distance between the red particle and the center of the local structure. Okay, so D less than 1 means it's actually inside the local structure, and then when it gets further away, D becomes larger. So if we measure that, what we see is that as we drop the temperature, the red is high temperature around the mode coupling temperature, and now we're going down in temperature to around 3 orders of magnitude slower than the mode coupling temperature, then the excitation particles are pushed progressively out of the local structures. So in other words, as we get colder and colder, this network of local structures becomes something that the excitations happen outside of. So in the last couple of minutes, what I'd like to do is just mention, can we do better with the structural measures? So, I mean, it looks okay, and of course, I've made sure it looks okay because I'm giving a presentation, but it would be nice if the structure, if, for example, the structures are a bit on-off. What I mean by that is, if I imagine I'm measuring this, I break one of these bonds, and then I don't measure this anymore. And the bonds are built around a Voronoi decomposition. So if the particles move a tiny bit, suddenly this thing disappears from existence, which is unsatisfactory. So what we could do, instead of measuring are we in one of these or not, let's measure the number of these that we're in. The particle in the center of an icosahedron is in 20 of these pentagonal bipyramids. So these are subunits of an icosahedron. So this is an example that I like. It's not glass, it's a nucleating crystal, but what you can see is that the white particles are in few of these, and the purple particles are in more of these. So we can measure the fivefold symmetryness of the liquid surrounding the crystal, and the crystal is killing the fivefold symmetry local to it. So this is an example where we can look at another way of looking at the liquid, in this case around a crystal. Here we've done it in our deeply supercooled experimental data. Here these cream particles are in 30 of these pentagonal bipyramids, and as we move away, then we get further away. So I mean, obviously it's still discrete, but it's moving towards a continuous field of, in this case, fivefold symmetryness. For the material that I've spent most of this talk talking to you about, the Cobb-Anderson model, this is not fivefold symmetric, it's actually fourfold symmetric. So the local structure here is this bicap square antiprism, and you see it here. It's got 4 membered rings, and so rather than the pentagonal bipyramids in the previous slide, here we have these octahedra. So it turns out that this bicap square antiprism is built of 2 octahedra sharing a particle and twisted against one another. So what I'm showing in this plot here is if I'm white, I'm in about 12 of these. The white particles are in about 12 of the octahedra, and the blue particles are in fewer octahedra. So this is another way of expressing the local structure. Is it time, Luca? Good. So this is a couple of reviews on hard spheres and universality in glass experiments. I talked about the topological cluster classification. I mentioned this dynamical phase transition in trajectory space, and this decoupling of timescales between excitations and dynamic heterogeneity. And I said that excitations are excluded from local structures, and I talked about a better way, or another way, to measure local structure in supercooled liquids. And so to summarize, it's looking good for facilitation, But how much of what we don't know is how much of the relaxation it's responsible for and how the excitations are correlated. And I'd emphasize that structured dynamics anticorrelations are enhanced at deep supercooling. And so with that, I'd like to thank you for your attention.
Thanks a lot, Paddy. Questions? Okay, well, let's go.
Great talk, Patty. In the Chandler picture, wasn't there a specific prediction for the temperature dependence of the number of excitations? Did you talk about that?
It's a brilliant question. It agrees perfectly.
Okay.
It's absolutely great. It's spot on. Almost all the predictions of the facilitation theory are upheld in the measurements we made.
I just wanted to make a quick comment on something I think you touched on and maybe implied, which is that if you have a model that's purely described by dynamic facilitation, so a kinetically constrained model or something, then there should be no correlation between structure and heterogeneity. But I think that's not true in that way, because in that sort of strict sense, because I can take, for example, a kinetically constrained lattice gas. I can ask for each particle what's its probability of moving within a certain time frame. That is a measure of dynamic heterogeneity. And that question is answerable knowing only the current configuration, which means that actually the structure of that configuration embeds all of the information about the dynamic heterogeneity, right? So the information is there, right, in spite of the fact that at equilibrium this thing has no structure, right? So I think that's something one has to be careful with logically. So even in a model that is completely described by facilitation, right, there must be a correlation between structure and dynamic heterogeneity. That is, in principle, that relation is discoverable by, for example, machine learning, etc. We don't know what those order parameters are, right? But I just wanted to make that general point that even if you have a model that's only facilitated and has no interesting Hamiltonian, it has a correlation between structure and facilitation or dynamic heterogeneity. So I think that's something one has to be careful with when trying to identify what's causal and what's not, right?
So Patty, the anti-correlation you talked about, can you just go back to that slide quickly? I didn't quite understand what the statement was. I mean, I guess that one.
What we're doing here is we're asking if the particle's in an excitation, is it also in a local structure? And then if there's no correlation, this quantity is 1.
Okay.
Okay. So at high temperature, well, it's not too far from 1. The more we drop the temperature, the less likely it is to be in both an excitation and a local structure.
Okay, so this is exactly what you would expect, right? I mean, that if you believe in the structure determining dynamics, that stable structures will determine more and more a slowdown, or
what I've removed from this plot is the CRRs, and actually the CRRs are much flatter. There's a slight, it's sort of like this for the CRRs. So the excitations actually have a much stronger coupling or anti-correlation structure than the CRRs do. I'm sorry, all right. So CRRs are cooperatively rearranging regions, which are a little bit the sort of picture in something like RFOT, where you have a cooperative region that's actually quite large or getting bigger and bigger as you drop the temperature. And these we measured as well, and they had much less relationship with the structure than the excitations did.
I think it's not on.
Yeah. So when you identify these excitations, you look for the step, and you also have a threshold waiting time before and after the step.
Yes.
Right? So if you're at very deep supercooling,
yes.
And you did say that you can misidentify excitations if they do drop back, right? They don't stay in the new step, in the new position, right? So at very deep supercooling, how does one unambiguously identify what an excitation is?
Actually, it works better at deep supercooling than at high temperature. I didn't mention this, but the algorithm kind of breaks down at temperatures higher than the mode coupling temperature. At deep supercooling, the algorithm that I mentioned works, well, it works fine. We use exactly the same algorithm for high temperature and low temperature, and we have relatively fewer fails when we there are fewer failed excitations at lower temperature than high temperature. Well, that's just an empirical observation.
Okay, so Giulio pushed me. So I'd like to comment on your answer to Mark about the facilitation predictions. So in the work that has been mentioned, where with the Cecilia Herrero, we measured again, there's two numbers that you need to reconstruct the relaxation time in facilitation model. It's how the energy scale with size, or this dynamic exponent, and the concentration of excitations. So when we measure those directly in the simulations to reconstruct by the Chandler-Gahan argument, the relaxation time, what we find is that the numbers in the Hedges paper 2011 that you mentioned, there's a gigantic compensation of errors. So the two numbers are wrong, but the combination of the two numbers is right. So I think what this seems to suggest is that the algorithm that has been used, that you have used to measure the concentration of excitations, it's not what, it's not wrong. It's giving you a number that scales with an Arrhenius, but the activation energy is very off. And we knew that from the 2011 paper because it's predicting dynamic correlation lengths that hopefully are wrong. So there is an internal self-consistency problem in these predictions that you say are working perfectly.
What we measured worked well, but we didn't do that analysis.
Okay, I think we should thank Paddy again. And we move to Sarika Bhattacharyya.
Where did my presentation allow? Yes. What do I do? Okay. Yeah. Thank you. Yeah. Good morning, everyone. I would like to thank the organizers, Ranjini, Shantan, I don't see him, Rituparna, and Shrikant, for inviting, first of all, organizing this meeting, which happened after a long gap after 2018, which Paddy organized, and also for inviting me for giving a talk here. So, yes, I will come to the title at the end of my talk, but before I come to that, this work is from this paper here, and the acknowledgement, Sanket and Mohit primarily worked on this project. Sanket is in the audience. Indrajit was a collaborator, and it's not like as long as ago, like Mahesh said, his work started, but this was a former student who actually started working on the project, and then eventually he became a collaborator. He is now in Kyoto University. I would give some introduction, which is probably for the students, but not needed for the others. I'll review many of the work of the people who are sitting in the audience. So probably they will not like my review of the work in the way I think about it, but let me just. So basically, when we enter a supercool liquid domain, the dynamics become slow, and the relaxation time can be fitted to either a VFT form or the parabolic form that Paddy has mentioned. And then with the slowing down of the dynamics, there is a heterogeneity in the dynamics which starts developing. This is an experimental picture of colloidal system. This is from Giulio and Lodovic's paper, like the review paper, where it's a two-dimensional system. You can see particles which are faster are clustered together, and there is a way to measure this dynamic heterogeneity, which was first introduced by Chandan. And the way the dynamic heterogeneity is measured, it shows that as you go to lower and lower temperature, the dynamic heterogeneity increases, and this gives rise to a dynamic length scale, which can be measured in many different ways. One of the ways is to do the 4-point correlation function, where you can fit it to a non-Stanzonic form, and you can see that there is a growing dynamical length scale, which can be connected to the way that relaxation time is. This is again coming to RA40 theory, that the relaxation time can have some correlation with this kind of a length scale, and it grows initially faster, and then there is a slowing down, which Paddy also has showed in one of his recent paper, but this is just one of the references where it's been shown that there is a slowing down of the dynamics, slowing down of the dynamical length scale. Now, what happens is there a growing amorphous order? And that's the question we are asking, that along with the slowing down of this length scale, if there is an amorphous order or structural length scale, and there are many theories and many different ideas about the growth of the structural length scale with the dynamical length scale. There is this frustration limited domain concept by Gill, and to quote him, he says that frustration describes an incompatibility between the extension of the local order preferred in a liquid and the tiling of the space. So this concept, as Paddy mentioned, started with Frank saying that there is a local ordering, which is an icosahedra ordering, and the system takes a while to understand that this is not a global ordering. And there are systems where there is no global ordering, there is no crystal structure, so these are these frustrated domains which stays. And here is a work from one of such systems where it was found that the dynamical correlation length grows much faster, like much stronger in terms of the density compared to the static length scale. Now, if these icosahedra structures are less frustrated when you curve the space, so this work Patrick is also there with Gill, and here the other Patrick is there with Gill, saying that if you curve the space, then your icosahedra order is less frustrated, and here the static and the dynamic length scale grows together, whereas here they don't grow together. And here is a plot of different degrees of frustration, and in some cases it grows well together, and in other cases it doesn't grow. Now, there is this work by most of them are sitting in the audience. So Smarajit, Chandan, Shrikant, Shiladitya, and Indrajit was here till 2 days back. They had shown that systems where there is a MRCO, that is medium range crystalline order, that system, the static and dynamic length scale grows in the same way, whereas this 2D Artin model, the static and dynamic length scale did not grow together because there was no well-defined MRCO. And here there is a 3D system, which is LFS-rich, locally preferred structure-rich system, where the static and dynamical length scale grows together. And then there is work by Paddy, which he mentioned a little. He didn't put this figure, though, that when you go to the deep supercool regime, you will see a growth LFS-rich regime where there is a larger number of icosahedras present, and there the static and dynamic length scale grows together. Now, if you think about the frustration theory and these last two slides which I presented, they are in tune. Like, it's basically MRCO is present when there is less frustration and not present when there is more frustration. And then there is this whole new different idea by Hajime Tanaka. He says that these are, of course, with MRCO, the G6, the hexactic order grows here. I think the icosahedra grows, and the static and dynamic length scale grows. But he has also introduced a generalized order parameter and showed that in these systems, the static and dynamic length scale always grows together. And I'm going to talk about Cobb-Anderson model, which is many of our favorite glass formers. And just a quick review of what happens in Cobb-Anderson model. This is Paddy's work again. He has shown that the dynamic length scale, and this is the LFS he has already introduced, so I don't have to talk much about it. It's twisted bicapped prism structure, anti-prism structure, where 11A structure is what I will refer to it as. Here you can see that the LFS does not grow, whereas the dynamic length scale grows. And there is this work from Ludovic and co-workers, showing that the point to set correlation length grows modestly, whereas the dynamical length scale grows a lot more. So then it appears that Cobb-Anderson model will fall in this class of system where there is more frustration between locally preferred structure, like more frustration, and the static and dynamical length scale will not grow together. Now, before I go into static and dynamical length scale, let me introduce you to the order parameter that I'm going to use. So this order parameter work started with Chandan when we were describing a mean field potential, it was a theory of trying to explain a mean field caging potential of particles. And I won't go into the details of the theory, but what we come up with in terms of the order parameter is that the order parameter here is described by a direct correlation product of a direct correlation function and the radial distribution function. What it tells us is how much the particle is caged. Each particle is caged. We can do it at per particle level. Each particle is caged, and we can show that this order parameter beautifully can capture structural heterogeneity. That means you can see more caged particles, less caged particles, and there is an evolution of the structural heterogeneity in terms of temperature. We are still above MCT transition temperature, so it's not like very low temperature, but you do see beautifully the structural heterogeneity comes up here. What we can also show is that particles which are in the deeper caging potential, which we call it hard, are slower than the particles in a softer caging potential. We also can see that particles which are fast have less well-defined structure, the red one, whereas particles which are slow have more well-defined structure. They are not identical. Here I've picked up particles which are in deeper caging potential. Here I'm just taking fast particles and looking at the structure, but this tells that the picture is consistent. Now, what we also could show is that this order parameter could show everything which this machine learning studies of Liu and co-workers had shown. And here is a reference, and one of them, and there are many. So here what we do is we plot the total number of particles, like the ratio of the fast particles by the total of number of particles. As a way we describe how the particle we call fast. And we see that this ratio has no dependence on the order parameter at high temperature, but as we go to lower and lower temperature, this ratio starts becoming dependent on the order parameter, which tells us that if a particle is sitting in a deeper caging potential, its probability of becoming a fast particle lowers down, whereas particle in a shallower caging potential become more fast. Now, the way we can write the same function can be plotted as a function of temperature. It has been shown that it shows an Arrhenius behavior, and it predicts there is an onset temperature here. This was first predicted by Liu and co-workers, and we could reproduce the same thing. What it tells us here is that we are talking about a local caging potential, and the picture of a caging potential is valid only below onset. So you cannot, the theory will break down above the onset temperature, so you can predict that, the probability of a fast particle becoming having higher probability to move slows down beyond onset, so the theory is valid only till the onset temperature. Now, we extended this work to experimental system. This was done in collaboration with Vijay, who is sitting in the audience, and his student Rati, and my student Mohit. What we had shown here is that, if you actually calculate it, we are calling it softness, but it's the same depth of the caging potential, the inverse of the depth of the caging potential. We see that the distribution of this order parameter changes as you change the density of the colloidal system. We could also show that particles which are faster, which are this red, this is a total distribution of the order parameter, and this is the particle which are faster. You can see they are sitting on the softer region of the caging of the order parameter. We could also show for sheared system, as we increase the shearing, there is a softness which develops, and here is a short movie to show that regions which were soft were the first activities started when you shear the system. So I kind of convinced you that this order parameter is a good order parameter to explain the dynamics. I'll now quickly, in one slide, try to understand what is its correlation with the locally preferred structure that Paddy has mentioned. Here is the probability distribution of the order parameter for all the systems. Here it is the probability distribution of this caging potential for the locally preferred structure. You indeed see that the locally preferred structure has probability of having deeper caging potential, but it's not that narrow. It's not like something here. We do see a lot of distribution. We were looking at the particles which are in this 11A structure, their dynamics of the particles. We also picked up, they were 12% of the total number of particles, so we picked up 12% of the hardest particle here and looked at the dynamics. So they are equally slow. So the particles which are in LFS might not be the hardest particle, but if I pick up the hardest particle, they are equally as slow as that predicted by the locally preferred structure. So now I'll explain to you how I do the dynamical and static length scale. We do the normalized excess correlation of the mobility and our order parameter, which is the depth of the caging potential, which is simply nothing but the product of CR and GR, if I write it in a simple form. And here is what we see, that the correlation changes a lot with temperature when it's a dynamical length scale. When it's the dynamics, whereas in terms of statics, the correlation, the increase in the difference in high and low temperature behavior is not enough. And thus, as expected, the static length scale does not grow as much as the dynamic length scale. And I'm sure all of you are happy till this point that I have shown the static length scale not growing like the dynamic length scale. Now, something I want to mention here, the dynamical length scale is always calculated at tau alpha, right? When we are looking at an order parameter, we are mostly looking at how is it connected. At least we did it like with the short time dynamics of the system and not the long time dynamics. So now if I actually calculate a correlation length, and Smaradit, it's not the same dynamical correlation length as you do. It's not the vectorial one. So if I just say that I want to calculate a dynamical correlation length at tau beta and not at tau alpha, then I find that that grows the yellow curve here, that grows similar to my static length scale. So which means if I didn't do the dynamical length scale, the mobility correlation at the long time tau alpha, but I did it at a short time, which is the tau beta time scale, I would have seen a similar growth of the dynamical and static correlation length. So this tells me that we need to rethink about our structural order parameter. The structural order parameter which was predicting the dynamics at short time is probably not the structural order parameter which predicts the dynamics at long time. Now, to do that, I would explain this coarse graining order parameter, which has been quite popular recently. So what you do is you don't take the order parameter value as such of a single particle, but you coarse grain over a length with an exponential weighting of how far you do the coarse graining, and you redefine the order parameter of that particle over. So basically, you try to take care of the order parameter by considering its neighbor's order parameter also. So there is a weighting of the neighbor's order parameter. And here there's a work by Tanaka, who has shown, Tong and Tanaka, who has shown that the correlation between the structure and dynamics grows for his order parameter if he does such kind of coarse graining. Here there is a work by Zhengang Wang, which is published in JCP, that the correlation of, this is a local volume. The local volume and the dynamics correlates poor at longer time, but the moment they do a coarse graining of the local volume, it starts correlating better with the dynamics. These kinds of coarse grained order parameters, using them as structural descriptor has become quite common in machine learning studies. Like Misaki has shown this, and Ludovic has shown that how at high temperature you find that L values, smaller L values are more important, but as you go to lower and lower temperatures, the order parameters with larger L values are more important. So now, how do I then describe my order parameter at different temperatures? Because I know that my order parameter at high temperature, at shorter time, high temperature or at shorter time is different than low temperature and also at longer time. So this is a prescription which was given by Tong and Tanaka, and we have kind of followed it. So we do isoconfiguration run. We look at the propensity, and we actually look at the correlation between the coarse grade order parameter and the propensity at different temperatures. And we do see that there is a non-monotonicity in a behavior. That means there is an optimum coarse graining length where the correlation between the dynamics and the structural order parameter, coarse grain structural order parameter is maximum, and that changes with temperature. It grows with temperature here. Now, we can calculate this L max, which is the maximum of this. Let's concentrate on the A particles now. And we can identify this optimum coarse graining length, and then we can redefine our structural order parameters in terms of this coarse graining length. So after doing that, here is what is a snapshot of my order parameter at a single particle level. Here is how it would have shown a growth in terms of temperature. Here is how the dynamic snapshot of the dynamics at tau alpha. Here is how the dynamics grew with tau alpha. And here is a snapshot of the order parameter, which is coarse grained. And here is how it would grow when I do the coarse graining, as I shown the prescription before. Now, doing this, I can show that this order parameter, which was not growing, it was sitting somewhere here, is now growing like the dynamical length scale. The length scale of the order parameter is growing like the dynamical length scale. And now the question is it a static or a dynamic length scale? I think that's where the question, I didn't put it up in the paper though, because that question was not asked by the reviewers, but I decided to now answer this question to the audience here. Now, I know it is not similar to the point to set length scale, but in that way, I think if you take any LFS and look at its order parameter, that is not the point to set length scale, right? Point to set length scale is telling us something different from a locally preferred structure's order parameter. And I will argue that it is not even a dynamic length scale, so somewhere it's in between probably. And to do that, let me go back and see what the coarse graining does. So I calculate a distribution of softness. I take the 10% of the hardest particle, and I look at the dynamics of that, and I showed that that time scale is as slow as that predicted by the LFS. Now I coarse grain my order parameter again, and I take 10% of my hardest particle, and I do the length scale, and it shows a slower length scale. I coarse grain my order parameter again, take 10% of the slowest particle, and I see it slows down again, and eventually there is a non-monotonicity that I coarse grain it further, and I cannot pick up the best slowest particle from my order parameter. So the Lmax tells me the best coarse graining length to pick up my slowest particles, and this is more so at low temperature than at high temperature. And the next thing what I'm going to show you is that this length scale is not same for both the A and the B type of particles. And in the same way, the length scale that we calculate, I don't know if we should call it a static or a dynamic length scale or somewhere statodynamical length scale, it grows less for the B particles than the A particles. And here is something I'll be able to connect to the frustration concept of Gilles. So if we look at this Cobb-Anderson model, we know that this Cobb-Anderson model around 90-10 mixture forms a distorted FCC, 80-20 mixture, and there's a lot of work done by Yepes group there showing that if you run it longer or if you take a bigger system, it undergoes a crystallization mostly by the A particles forming an FCC crystal structure. And we had also done some analysis by doing a biased Monte Carlo simulation. We could show that here is the growth of FCC structure. There is this barrier for FCC formation. We could never find a barrier for CSCL formation even in biased Monte Carlo simulation. If you put a CSCL crystal seed there, everything around it would grow as only FCC and not a CSCL structure. So if I had to see a barrier, that barrier would be probably somewhere sitting there or infinite barrier. So this 80-20 mixture has a tendency of FCC formation, and the reason behind it is that there is a compositional frustration. It is no more the space, the curvature of the space, but it's a composition which frustrates the system to undergo a CSCL like crystal structure formation. Whereas if I move more towards a 60-40 mixture, and here I'll show you something which we had done at 5842, we do see an instant crystallization and a BO related to the CSCL structure comes up there, which means that my 60-40 mixture is sitting very close to a CSCL formation tendency, although we do not find any LFS from these, either the 80-20 or the 60-40, which will show me some kind of an FCC or CSCL formation tendency. But I know there is a frustration, and the frustration can be reduced if I change the composition. So what we do here is we do a 60-40 mixture, and I find that this L max, which is the max coarse graining length, grows similarly, and this length scale that I call a static length scale of the A and the B particles grows like the dynamical length scale of the system. So then, what about time? Almost, yeah. So basically, this is something I mentioned here, like this is after after Jill's talk, I thought of including it is the mobility, the propensity at tau alpha. Right. Yes. So it is. Wait. So that's the reason I showed you the previous thing, that I don't look there. Look here. I know you're looking for more people to say the same thing, but no. But let me tell you something. So what I try to tell you is, if you have 100 LFS, right, and you pick up which is your best LFS, you also look at which is the longest living structure, right? So you actually have some kind of a dynamic information even when you're picking the best LFS. Not about point to set, but even in an LFS, you actually need the information of the dynamics to understand which is the best LFS in your system, right? Paddy, am I correct in that? Yes. So I'm doing the same thing. I have 100 order parameters, and this is something I had shown a little, like maybe I can come back to the question answer session. Okay, so now here was the length scale here, but what I did here was I looked at the mobility at a short time, at tau beta time, and I correlated with the mobility at a longer time, and I found the same length scale which is coming up, which came up when I kind of connected, like correlated my coarse-grained structural order parameter with the propensity at tau alpha. So this is something which probably what Paddy was trying to say is that, and I also think, there is a part of dynamic facilitation here, that particles which there is a mobility at tau alpha, which eventually can be a single particle's mobility at tau alpha will not describe this mobility of the particle at a longer time, but you need to understand the mobility of your surrounding around you, and as a whole you probably will move longer at, so there is kind of, it can be a facilitation to slow down on your dynamics, it can be a facilitation to speed up the dynamics, but either way the neighbors will start contributing to your long time dynamics, and the same length scale that we get out from here comes out from this thing. So this is a question which is in the discussion part of the thing. We can discuss and see if this is something telling us about. So now what I tried to say is this coarse-grained length scale of the structural order parameter grows like the length, I would call it a static length scale though, like the dynamic length scale. It is not the point to set length scale, but again I'm arguing that all the length scale you get from LFS, you know, it doesn't grow, you're happy, you don't complain that it is not the point to set length scale, but if it grows, then I'm trying to do something like the LFS, I'm taking many structural order parameters, and I'm trying to pick up which best describes my slow dynamics, and it can capture the frustration, which I don't think a dynamical length scale would do, at least I haven't seen any dynamical length scale capturing the frustration. We are trying to extend it to systems with hexatic order to see how it works. And it would be best to get this length scale without getting the information of the dynamics, and that's probably what we would try to do next. with that, let me thank you for your attention.
Thanks, Sarika, for the nice talk and for being, I think, the only person who really kept time since the beginning of the conference. So we have time for questions.
Yeah, so maybe I'll show what
I should have not
wanted
said
to.
that.
Yeah, where is that slide? Yeah, so this is what I was trying to tell you, Shaurajit, that you can think about it in a little different way, that you have many LFS to you. Don't even, it's not an LFS, but many order parameters. And amongst those order parameters, you want to see which is best describing your slowest dynamics. Then you would be able to pick up the same value of the order parameter. It's coarse-grained, of course. I can put a single value of an order parameter, I can put a coarse-grained value of the order parameter, and I can see amongst this order parameter at that particular temperature, which is going to best describe my slowest dynamics, and it will automatically come out that the coarse-graining length, which order parameter would best describe the slowest dynamics, will come out from there.
I'm trying to think of, is it static lengths or is it the dynamic lengths? So I'm trying to organize this in my head. I mean, I think it depends I would say, of what is the mechanism that controls the slowdown, right? If the mechanism is a static mechanism that, by definition, what you will measure would be a static length scale. If the mechanism is that it's related to the dynamic facilitation length, that you will measure dynamic length. So, in a way, what you're doing is something which depends of what, it's not telling us what's the mechanism that's slowing down. It's a length scale that it's just slave to that mechanism. It's the same as when I think Smarajit and maybe Tamara and others looked at the finite size effect on the time scale. Then the size is it's a length, right? But it is a static length if the mechanism for slowdown is a static one. It is a dynamic length if the mechanism for slowdown is a dynamic one. I think that would be the answer. I mean, it's not helpful, but I think it helps.
Yeah, no, I agree. Maybe. And I have been, the last slide was put up after your talk, and I think I didn't put any dynamical facilitation in my paper, but it's just the thought, but I think they're connected. The reason is, at short time, what we find is the structure and the dynamics are quite strongly correlated at a single particle level. Now, what I'm trying to say is the structure, if I want to understand the long-time dynamics of the system, the structure alone cannot predict my long-time dynamics. I would need the information of the structure of my surrounding particles. I'm just saying that. I'm not yet going to the dynamics of my surrounding particles, but in turn, the structure of the surrounding particles are also connected to the dynamics of the surrounding particles. And that's the reason, effectively, it would be also the dynamics of the surrounding particles which will affect my dynamics at the long time. And this is probably the growth of that, kind of what probably Paddy said. I haven't gone to deep supercooling, but the number of particles, the number of excited particles you need to have for a particle to move a long distance will keep increasing as you go to lower and lower temperature, so that length scale grows. But it is also connected to the structure, because eventually I'm just doing a structural order parameter and its correlation. But I think it is good time for the community to think, what does the coarse graining structural order parameter mean? Because it's been used a lot in machine learning studies now to predict the propensity better. What it would give or what it would mean is something good to think about.
There was a question over there.
I have two questions actually. The first one is the way you define the tau beta and you relate it to the structural length scale. The length scale that you relate it to. So it seems to grow equivalently. So my question is that other length scales, if you compare it with the way you are defining the short time dynamics and the...
this one?
No, not this one. So you relate
okay, the tau beta.
Yeah. So
the length scale related to tau beta.
So what I believe is that the PTS will also grow similarly?
So PTS grows a little more, the best PTS which we picked up.
Okay. So
which is
so my
Ludovic's,
question is that, does PTS also, like the structure related to the PTS, does it also define the short time dynamics? The
no,
tau
there
beta?
is no structure related to PTS. The PTS concept is very different.
The length scale that you derive from PTS?
Yeah. So I haven't derived anything. It's just taken from previous work. But what I'm trying to say is, what PTS tells us is, if this within this range, if the cluster of particle by themselves can change their position in phase space, right? That's what is PTS. It doesn't look at the locally preferred structure or anything. So what I will so I don't know if there is if there is a structural, like there is a locally preferred structure. No, nothing like that.
No,
that concept doesn't come in PTS.
No, the length scale that is derived from the PTS, say,
Yes.
can that be mapped into the way you define the tau beta?
So it would kind of, a little less maybe, because this is my green here is what I would have, I have to go back to that slide.
No, that's fine.
Yes.
That's fine.
So this is the PTS length scale, and the tau beta is following the structural length scale without any coarse graining. So it is still lower than the PTS length scale, but they are mapping onto each other. Yeah. I'm not doing the finite. I'm just doing the way I do. No, I understand, Shaurajit. Those are your static length scale calculation. Here I'm talking about this as a dynamic length scale. If I had done the dynamic length scale at the better relaxation time without going for your vectorial way of doing it, I would have got, just like I've got the red line here, I would have got the green line here by doing the scalar displacement correlation function. That's what I'm arguing.
Okay, I think that in the interest of coffee break,
Yeah.
we should stop here. Thank again Sarika and all the speakers. And I guess that we can still be back by 45 so that we don't get too late for lunch.
You have to switch it off. Rajini, you know how to switch it off?
Yeah, there are switches everywhere.